Welcome to the sixth session of our topic on global challenges confronting the United States. And also welcome again to our Osher colleagues up in Burlington at the Osher at University of Vermont. A reminder once again to please turn off your cell phones. We will also have a book signing at Intermission. Our speaker's very short but very effective book called What We Know About Climate Change will be on sale down the hall towards the cafeteria during intermission. The price is $16.95. I hope they have a lot of nickels sitting around. As always, please write your questions on the cards and bring them down to the front during intermission. And now I'd like to thank our underwriters and sponsors. The Jack and Dorothy Byrne Foundation, Caldwell Law, Kendall at Hanover, Ledyard Bank, Wells Fargo Advisors, and this week's sponsor, Dartmouth Hitchcock. And with that, I would like to invite Ann Hargraves, who is our session moderator today, to come out and introduce our speaker. Ann?
Good morning, everybody. Kerry Emanuel is a prominent meteorologist in climate science, specializing in moist convection in the atmosphere and tropical cyclones. He is the Cecil and Ida Green Professor of Atmospheric Science at the Massachusetts Institute of Technology and co-founder of the MIT Lorenz Center, which is a climate think tank fostering creative approaches to learning how climate works. His interests also include cumulus convection, the role of clouds, water vapor, and upper ocean mixing in regulation of climate and advanced methods of sampling the atmosphere in aid of numerical weather prediction. Emanuel received an SB degree in Earth and Planetary Sciences and a PhD in meteorology, both from MIT. After completing his doctorate, he joined the faculty of the Atmospheric Sciences Department at the University of California at Los Angeles, where he remained for 3 years, with a brief hiatus filming tornadoes in Oklahoma and Texas. Perhaps he'll tell us a little bit about that. In 1981, he joined the faculty of the Department of Meteorology at MIT and was promoted to full professor in 1987 in what has since become the Department of Earth, Atmospheric, and Planetary Sciences. In 1989, he assumed directorship of the Center for Meteorology and Physical Oceanography, a post he held till 1997. Subsequently, he chaired the program in Atmospheres, Oceans, and Climates from 2009 to 2012. He is co-founder of the MIT Lorenz Center, which is a climate think tank which fosters creative approaches in learning how climate works. Professor Emanuel is the author or co-author of over 200 peer-reviewed scientific papers and 3 books, including Divined Wind, The History and Science of Hurricanes, and What We Know About Climate Change, published by the MIT Press. He was named one of Time's 100 Influential People of 2006. In 2007, he was elected as a member of the U.S. National Academy of Sciences and was recently elected to the American Academy of Arts and Sciences. He is an honorary fellow of the Royal Meteorological Society. Please welcome Professor Emanuel.
Thank you so much. That's great. Well, thank you very much, and thank you, Anne, for your very lovely introduction. It's wonderful to be with all of you here this morning. I must say, I'm surprised to see so many of you here. If this kind of event had been hosted at my home institution of MIT at 9 o'clock in the morning, there'd be about 5 people in the audience. And they would be students who had extended their all-nighters by an hour. So thank you for coming. So today what I'd like to do with you is to kind of give you a little tutorial on the latest developments in climate science and also the history of science, and kind of end up at the end with a serious discussion of how we might go about tackling this problem, because I think this is the widest gap. Here lies the widest gap between what professionals believe is possible and what the general public believes is possible. And I want to try to paint for you a picture in which the future is not something to dread, but is something that could be very exciting. So I'm going to start off just by giving you a roadmap of where we're headed today. These are the main points I'd like to try to make to you: that the Earth's climate is stable within certain limits, but it's sensitive to changes in what we call forcing, radiative forcing, within those limits. Climate science is not new. It's been around for well over 100 years, and I'd like to talk to you a little bit about some of the figures that were very important in the history of climate science and what they discovered. I think you may be surprised that some of the things that we talk about today were well known more than 100 years ago. The idea that we collectively are altering climate is based on relatively simple physics and simple models. And it is only in the modern era that we've been able to supplement this with complex models. Human activities can and do have a strong effect on climate, and I'll try to explain to you why that's so, and that this is actually a very old idea, not a new one. We're beginning to be able to quantify, to actually put numbers, probabilistic numbers, on some climate-related risks. And this may sound slightly Machiavellian to you, but I'm serious about it. Where there's risk, there's also opportunity. And I'm going to try to focus at the end of my talk on what those opportunities are. So let's begin with climate science, and let's talk a little bit about the history of the Earth's climate. And I'm going to begin by showing you this graph, which is taken from one of the great ice cores that paleoclimatologists have collected. And I happen to feel that the field of paleoclimate has been enormously successful, and it's kind of an unsung accomplishment of science in general, that we've been able to figure out so much about how the Earth's climate has varied in the past. So what you see on this record, which begins on the left 450,000 years ago and ends more or less today, are cores from different places in the Arctic and Antarctic that show at the top records of temperature. And so where you see it going up, it's relatively warm, and where it goes down, it's relatively cold. And the red curve at the bottom is a measure, and you might start thinking about how we could possibly know this, of the volume of ice on the planet. And this one is a little bit different because low volume is on the top and high volume is on the bottom, so it's sort of flipped upside down. But you can see that the two are very well correlated. When it's warm, there's not much ice. When it's cold, there's a lot of ice. And that in this 450,000 year period, there have been 5 relatively warm periods, of which we are in the most recent one, and in between which is quite a bit colder. Now, as you're probably aware, during those cold periods, particularly in the northern hemisphere, much of the continents were covered by ice. So in North America, we had the Laurentide ice sheet. This is a recreation of what that ice sheet looked like at its peak about 20,000 years ago. And by the way, 20,000 years ago was a blink of an eye geologically. It's nothing at all. 20,000 years ago, where we're all seated or standing today, was under about 1.5 miles of ice. That's a lot of climate change, okay? So the Earth's climate does vary dramatically. Now, this chart is showing the progress since the peak of the last glacial period, about 20,000 years ago, to today. So that's a graph in thousands of years, 24,000 years to the present. This is sea level. This is meters relative to the sea level today. So 20,000 years ago, the sea level was about 130 meters, almost 400 feet lower than it is today. That's rather spectacular. If you were in Boston and you could crawl out from under the ice sheet, you could walk across Cape Cod Bay to Provincetown and not get your feet wet. That's a lot of sea level rise. You'll also notice that the sea level came up and reached its current levels about 7,000 years ago. And in the last 7,000 years, sea level has been, by geological standards, remarkably stable. Now, it's probably not a coincidence that it was about this time that modern human civilizations developed. Of course, human beings as a species had been around a long time before that. But this is when we settled down, we began to develop agriculture and so forth. And one of the points I'd like to make to you is that we as a civilization are very finely adapted to the climate we've had during this remarkably stable period in the last 7,000 years. Sometimes people say, well, you know, how do you know that this is the ideal climate for us? I think that's somewhat irrelevant. The point is not whether this is in some global sense an optimal climate. It's the climate we're adapted to. And when we put buildings right down to sea level that would not tolerate any kind of change of the magnitude you see on this diagram, right? A 400-foot change in sea level would be catastrophic to human civilization. It was nothing to our forebears because we didn't have cities and towns and things like that. In fact, people just migrated without even really being conscious of it. But it's a different story today. We're very well adapted to the climate that we have. Now, we actually understand, one of the great accomplishments of climate science, we understand why we have these glacial cycles, of which there have been about 10 in the last 3 million years. And one of the early scientists who came to understand this was this Serbian mathematician, Milankovitch, who understood that the Earth's orbit around the sun varies over time. It's an elliptical orbit, it's not circular. The sort of degree of ellipticity, the length to width ratio of the ellipse, varies on a time scale of about 100,000 years. The Earth's rotation around its own axis, the axis rotation, wobbles like a top. There are changes in the obliquity, and that period is about 41,000 years. And then, like a top, also the Earth's axis rotation precesses around like that with periods of 19 and 23,000 years. Now, what those orbital variations do is they don't actually change the total amount of sunlight reaching the planet by very much at all. What they do change is the distribution of sunlight with latitude. So I'm going to show you a rather remarkable, if somewhat complicated chart. This goes back a million years. So this is a million years ago to the present. And there are two quantities that are plotted on here. In the red is the amount of radiation received in the Arctic from the mathematically known wobbles of the Earth's orbit. Okay, these are the Milankovitch curves. And you can see it varies up and down. The black curve that you see there is some entirely different measure. It's a measure of the time rate of change of the ratio of two isotopes of oxygen in the shells of ancient organisms collected from deep sea cores. This ratio of oxygen remarkably tells you what the volume of ice is on the planet. I don't have time to explain that, but perhaps someone would like to ask a question in the Q&A about that. It's a really interesting accomplishment. It's a very, very definite reading. And look at how well those two are correlated. Milankovitch could never have dreamed that his hypothesis about why there are ice ages could be so beautifully verified today. Right? We know why there are ice ages. We don't know everything there is to know about them, to be sure, but we basically understand why the Earth goes in and out of these. And if we weren't tampering with the climate, we would start slipping into another ice age in the next 10,000 years or so. Now, here's another very interesting personality in the history of climate scientists, the Irish physicist John Tyndall. Like some of the great scientists of the 19th century, he was a polymath. He dabbled in all sorts of things. And he was fascinated by Earth's climate and convinced from some earlier work by the French scientist Jean-Baptiste Fourier that the Earth had a greenhouse effect, and he set out to actually measure it. And so what he did was to build this apparatus, is basically a long tube, and he could create a partial vacuum in that tube, and then fill it with various gases of his choosing, like nitrogen and oxygen, the principal constituents of our atmosphere, and then shine a light through the tube and measure how much of that light was absorbed by the gases in that tube at various wavelengths. So he was the first scientist to quantify the greenhouse effect of the Earth's climate. And basically the way this works, by the way, is that there are gases in the atmosphere that absorb radiation, infrared radiation, trying to escape to space. They absorb it, and they re-radiate some of that heat back down to the surface. So the surface of the Earth is warmed not just by sunlight, but by infrared radiation coming from the atmosphere and clouds within it. The remarkable thing is this greenhouse effect is so powerful. On average, day and night, averaged over a year and average over the planet, we get almost twice as much radiation from the atmosphere as we get directly from the sun. Twice as much. All right? That's a very powerful greenhouse effect. Tyndall knew that, but he didn't know which gases were responsible. So that's why he built this. And the results he got were, even by today's standards, startling. And if you don't study this kind of science and you stumble on these, you just find it hard to believe, but they're fantastic. The first thing he discovered, the first thing you would do if you had built this apparatus, is you start with the main gases in the atmosphere, oxygen and nitrogen. Those are molecular species. They're symmetric molecules of oxygen, 2 atoms of oxygen, O2, 2 atoms of nitrogen. And argon is actually the next most plentiful gas. But they make up together 99% of the mass of the atmosphere. But Tyndall discovered that they don't do anything at all to radiation. They don't absorb anything, basically. So he said, gee, there's this big greenhouse effect. I put these 3 most prominent gases in it as nothing. They didn't absorb anything virtually at any wavelength. So he started working his way down the list and discovered that water vapor, which is a triatomic molecule, 2 atoms of hydrogen, 1 of oxygen, carbon dioxide, likewise triatomic, nitrous oxide, and a handful of other trace gases, absorb very, very heavily, particularly in the infrared part of the spectrum. So he actually did discover, ultimately, which gases are responsible for the greenhouse effect. And without these gases, if we took them away, even though they're less than 1% of the atmosphere, the mean average global surface temperature would drop from its current value of about 60 degrees Fahrenheit to 0 degrees Fahrenheit, and we wouldn't be here to talk about it. There's nothing controversial about this, by the way. Nobody in science anywhere would dispute that. We're here because of greenhouse gases. The startling thing about John Tyndall's finding is that the greenhouse gases that are really responsible are a tiny fraction. So here's what it looks like on a pie chart. There's nitrogen, there's oxygen, the green is argon, the greenhouse gases are that orange sliver. Can you see it? Yeah, in there, the front rows can see it, I think. The back rows may not. We live because of that orange slice. All right? That's pretty remarkable. And it is not controversial in science, not remotely. So that orange slice makes a difference between 0 and 60 degrees. But it's even more strange than that, because the most important part of that orange slice is water vapor. And water vapor is about 0.25% of the mass of the atmosphere, but it's most of the greenhouse gases. But it works very differently. It responds on a very quick time scale to temperature. It's basically controlled by temperature. So if I change the temperature, if I heat the atmosphere, I get more water vapor. If I could suddenly double the amount of water vapor in the atmosphere, it would quickly start to rain out, and 2 weeks later it would be back to normal. So it's not a long-lived greenhouse gas. It's a very short-lived greenhouse gas, short residence time in the atmosphere. It doesn't control anything. It's a feedback. So if by some other means I were to cool the atmosphere, there'd be less water vapor, less greenhouse gas. It would get colder yet. Same thing if I warmed it. So therefore, the climate is really controlled on time scales more than 2 weeks, which means all climate, basically, by the long-lived greenhouse gases, which are primarily carbon dioxide, methane, and nitrous oxide, and they together constitute 0.04% of the atmosphere. I wouldn't even try to put that on a pie chart. Nobody could see that. They're the controlling gases. And that's very, very counterintuitive to people. How could our climate depend on something so tiny? It's a little bit like, you may live in a house and it has a furnace. Well, I hope it does if you live here in New Hampshire, and has some means of heating it. And at least in the old days, the temperature of the house was controlled by a thermostat, and the thermostat was a tiny little glass enclosure that had a little bead of mercury in it. And you could say that that bead of mercury controlled the temperature of the whole house, all right? You understand that. It's a little bit like that. It's not the thing that's forcing things, it's the control. Now along comes another very grim-looking Swedish chemist, even grimmer than John Tyndall. What is it about climate scientists? They look so unhappy all the time. Maybe they were abused even back in their time, I don't know. But so he lived from 1859 to 1927, won a Nobel Prize in chemistry. But like many 19th century scientists, dabbled in all sorts of areas, and he was interested in this. He recognized, being a chemist, that we were just beginning to burn oil and gas back then, that if we started to do this in a serious way, we would actually increase the carbon dioxide content of the atmosphere. And he actually went and took measurements very, very ingeniously. Remember, no computers or anything back then. And discovered that, and wrote a paper, that if you were to double the amount of carbon dioxide in the atmosphere, you would raise the Earth's temperature by about 4 degrees centigrade. And if you were to increase it fourfold, you would go up by 8 degrees. And those numbers are remarkably consistent with modern estimates. And these were made 100 years ago. Okay? So there's nothing really new about that. Now, in essence, Svante Arrhenius made a prediction. And we can go back and say, is that prediction got any merit? Does it happen? Now, he thought it would take 1,000 years for us to double CO2. He didn't really, who could, predict how quickly the Industrial Revolution would accelerate. But the essence of his argument was double CO2, you're going to get a temperature increase. Well, here is a record going back to Arrhenius' time, the end of the 19th century, of the carbon dioxide concentration of the atmosphere. We know this by examining bubbles trapped in ice cores, and in the modern era by direct measurements, mostly from Mauna Loa in Hawaii. So that's the blue curve, is carbon dioxide. The green curve is the annual global mean surface temperature of the planet. And there are a lot of wiggles and squiggles. There's a lot more going on than CO2. There are volcanic eruptions, changes in sunlight. By and large, though, as Arrhenius predicted, the temperature is following the carbon dioxide concentration. This is not really rocket science, folks, and it's not depending upon complicated computers. It's just basic physics. Now, if we can go back using ice cores and examine bubbles of gas trapped in those ice cores much further in time. So this is a chart going back 1,000 years in ice cores showing carbon dioxide concentrations in parts per million. So in this era before the Industrial Revolution, we were about 280 parts per million. And then starting in the early part of the 19th century, we really started to accelerate burning of coal especially, then oil and gas, and the carbon dioxide concentration went up. It's now off this chart just a few years later. It's going up very, very fast. And there's no question about why this is happening. There's, again, nothing about what I've said to you so far today is remotely controversial within the science. We can go back much further than that. This goes back to the peak of the last glacial era, again showing carbon dioxide concentration, okay? And if you go back to when there was a lot of ice, the concentrations were even lower. They're about 180 parts per million. So carbon dioxide does very naturally during glacial cycles. And so what you're seeing here is a natural increase of carbon dioxide that occurred when the ice melted. It was then very stable, and that spike that you see there is man-made. And this is the same kind of chart, but for another greenhouse gas, methane. That star you see at the top is where we are today. Okay, we just sailed past 400 ppm. This is the Industrial Revolution, and it's brought great benefits to mankind, make no mistake of it, but it does have the side effect of putting a lot of very important greenhouse gas in the atmosphere. Now, we can also look at records of temperature from paleoclimate evidence, and this is a chart of Arctic temperatures going back 1,000 years. So this is literally 1 AD. And what you see here with some gray showing you the uncertainty in these measurements is temperature relative to what it was in 1 AD. And you can see that it's actually slowly in decline. And this is the natural reduction of Arctic temperatures that occur during the Milankovitch cycles. And if we didn't do anything, over the next 5,000 years or so, we would eventually go off a cliff and go into another ice age, 5 or 10,000 years. But what you actually see happen is, again, starting in about 1800, this uptick in temperature and a rather spectacular increase at the end of the record. Okay, that's not the Milankovitch cycles. It's much too fast. That's the effect of the carbon dioxide. Now, we've been measuring temperature with thermometers accurately over the globe only in the last 100 years ago. And what I'm showing you here is a bunch of measurements, again using real thermometers, going back to about 1750. And the gray shading shows you the uncertainty in global average temperature. It was huge back then because there were so few thermometers around the globe, but there are more and more. And by about 1900, we started to have really good estimates of global temperature. The different curves are just different estimates by different groups of researchers. And by 1950 or so, it was really rock solid. And this increase you see here is what we believe to be the man-made component of the temperature increase. Now, with satellites, we can start to see patterns of these increases. So this is the trend in the temperature of the lower part of the atmosphere from 1979 to 2012, based on satellites. It's not globally uniform. It was never predicted to be. It's most prominent at high latitudes and over continents. So that's why the Arctic specifically is sort of the canary in the mine for climate change. And there are even some places, like here and here, where it's cooled down over that period. This is because the Earth is a complex system. It's responding to uniform warming, but in a complex way, in ways that we pretty much understand. How do we know this is carbon dioxide? Well, one of the ways that we know that is if we look instead at the temperature of the upper stratosphere. This is way up at 50 kilometers altitude or so. That's on the bottom. It's going down everywhere. It's cooling rather spectacularly. That was predicted. It turns out that when you put carbon dioxide in the upper stratosphere is the main way that the stratosphere emits radiation to space. It gets heated by direct absorption of sunlight by ozone, but it is cooled by CO2, and this cooling is consistent with the fact that CO2 is increasing. If the warming we had seen was due to something else, like increasing sunlight, then the upper stratosphere would also be warming, and it's not. All right, that's a fingerprint of CO2. Now, this is a chart showing the heat content of the whole ocean going back to about 1970. And so what you see is the heat content of the whole Earth system has been going up. The amount of energy that goes into the oceans is in blue. The amount of energy going to everything else, most of which is the atmosphere, is red. So the important message of this chart is most of the excess energy trapped by the excess greenhouse gases is being used to heat the oceans because the oceans are much more massive. And they also introduce a big time lag into the system. The atmosphere is kind of the tail of this dog, if you will. We see other changes. The amount of sea ice covering the Arctic oceans has been in decline. And this is a chart going back to 1950 in red showing the square kilometers of sea ice in September, which is the month in which it reaches its minimum value in the annual cycle. This is a prediction by computer models, run both forward and backwards. And you can see that the sea ice has been dropping more precipitously than our models had forecast. And the history of science is a history of deeply little c conservative views. We don't like to make wild predictions in science. It's a good way to destroy your reputation, and we tend to be conservative. This is an example of things changing faster than they were predicted to. Alpine glaciers have been changing. This is just a photograph of a glacier in Washington State. I kind of chose this at random, 1973. And then a photograph of this from the same vantage point, more or less, in 2006. All the ice is gone. This is just a record of European alpine glaciers, the total mass of ice in those glaciers going back to 1946. A few of them, 2 of them, have actually undergone an increase in ice mass. Everything else is going down more and more rapidly as time goes by. There will be no snows left on Kilimanjaro in a few decades. It's almost all gone, okay? Hurricanes are changing. This is my own specialty. This is a graph showing the distance from the equator at which hurricanes reach their peak, going back to 1980. This is the same thing for the southern hemisphere, and in both hemispheres, the latitude at which hurricanes reach their peak intensities have been getting higher, which is not good news for middle latitude cities, but it is good news for cities deep in the tropics. This is something that's not talked about nearly as much as it ought to be, but there's a direct effect of carbon dioxide that actually has nothing to do with climate. As you increase the atmospheric concentrations, you dissolve more CO2 in the ocean. That makes them more acidic. And this is posing a threat to microorganisms in the ocean, including corals and plankton, which build shells and which are susceptible to the acidity of the water. We know from trying to grow those shells in controlled conditions in the laboratory where we can artificially vary the amount of carbon dioxide that if we get too much more in the ocean, we're really going to see, and we're already beginning to see, the disintegration of things like reefs. So if you're a diver and you like to see coral reefs, go soon before it's too late, because they are being visibly damaged now. Now, as I keep stressing to you, we understand climate basically from the proposition of physics. And the ideas that we're undergoing risk do not depend on hopelessly complicated models. Very simple models that you could run on your own laptop that really just are solving very basic physics can be used to do this. So this is a model we have at MIT that was developed for entirely different purposes, but what we can run that into sort of global temperature estimates. And this shows the surface temperature as a function of carbon dioxide, and this is just the number of doublings of carbon dioxide. So that's 2, that's a factor of 4, 8, 16, and so forth. The radiative forcing of carbon dioxide, for those of you with a math background, goes as a logarithm of the CO2 content. It's not linear in CO2. And we get about 3 degrees per doubling, which is right in the middle of the IPCC estimates of 2 to 4.5 degrees. And remember, Arrhenius's estimate from 100 years ago was 4 degrees. But we do have global climate models, which are useful for understanding some of the regional variations, for example, climate change. This is an attempt by those models to hindcast, if you will, the temperature, the measured temperature of the 20th century. So we're going back to 1890 or so here. The black curve is the observed global mean surface temperature. The red curves with the background pink are attempts to simulate them with modern climate models, the pink shading showing you the variation among the models. The blue curves are the same models but run without any anthropogenic influence. And you notice that you simply cannot come close to capturing what we've seen in the last 50 years or so unless we put in those anthropogenic influences, most of which is carbon dioxide. All right, so much for the past. What about the future? Well, as the great Danish physicist Niels Bohr said, prediction is very difficult, particularly when it concerns the future. And we're not we're not cocky, overconfident people that we're sometimes made out to be in the press. And if you go to a scientific conference, it's all about uncertainty. And what are the sources of uncertainty? Well, we don't understand clouds very well. Clouds are really important in climate. They reflect sunlight, but they're also greenhouse agents. They trap infrared radiation. So they work both sides of that street. And they're very complex. If you've ever looked up at the sky, you don't need to be told that. Water vapor, I mentioned to you earlier, is a feedback. If you warm the atmosphere, you have more water vapor. That makes it even warmer. But the details of that are not very well understood. The response of the ocean, particularly the very deep ocean, we don't have very many measurements there. It is not properly understood. And then there's another man-made player in this, which are aerosols, particles in the atmosphere that create hazes, which are highly reflective and tend to cool the planet. And so when we make projections, we aren't just saying it's going to warm by a certain amount. We have to create a bell curve like the one that you see here, which expresses the probability, in this case, of temperature increase in response to doubling carbon dioxide. So this is 1 degree, 2 degrees, 3 degrees. And you see the most probable is sort of in the range of, say, 2 to 4 degrees, just as IPCC said. But there is some small probability that it will be a lot less than that. And there is not such a small probability that it will be considerably greater than that. There's a small probability that it will be way out here. And if it's way out here, that would really, really be catastrophic. Nobody would doubt that. Fortunately, it's low probability, but it depends on what you mean by low. You know, we're talking about 10% or so. Is that low? I mean, would you let your kid cross the street if there was a 10% chance that he or she would be run over? I don't think so. So we have to be cognizant of that whole distribution and not just talk about the mean. Unfortunately, right now we're on track to do much more than double carbon dioxide even by the end of this century. So these are projections of the carbon dioxide concentration going out to the end of this century under various different assumptions about what we will do collectively. If we don't do anything, we're going to follow this purple curve, and by the end of the century, by the way, that blue dashed line is doubling CO2. So we're up to well more than tripling it by the end of the century if we don't do anything. And that will put us into that tail, very likely put us into that tail of the doubling distribution. So what's the problem with that? Well, you know, if it gets a little bit warmer, even Sven Arrhenius, because he was a Swede, said, hey, it'd be great when it's a little bit warmer. Well, it probably will be great for Sweden. There will be winners. One of the things we worry about, maybe not the most important thing, but a very influential thing, is the rise in sea level. So current estimates are by the end of the century between 1 foot and 4 feet of sea level rise. Well, if you go down to the waterfronts of San Francisco, Boston, New York, pick your favorite coastal city, it's not very tolerant to sea level rise of this level. It's not just the mean level that's of concern, but whenever you have a storm that creates a storm surge, it's going to be riding on an elevated sea level. That, again, is sort of the canary in the mine. You're first seeing these effects through the storms, just producing more flooding than they used to. You're already seeing that in many places. Now, one of the problems we have, which is a technical one, is that it's very hard once you put CO2 in the atmosphere. It's very hard for us, and it's very hard for nature to take it out again. So this is a curve showing, again, projections of CO2 content, but going out 3,000 years. There are a bunch of curves here, and it's assumed that when you get to a certain concentrations, 450, 550, 650 ppm, in these projections, it's assumed we're just going to totally turn off emissions of CO2. It's obviously hypothetical, but just to watch what would happen. And what happens to CO2 is it does precipitously drop over 100 years or so, but then it levels out, and it takes thousands and thousands of years for it to go back to normal if we were to stop. And if we go all the way up to 1,100 ppm or 1,200 ppm, we're going to be stuck with very, very elevated CO2 for a long time. This is the same curve, but looking at the temperature response. There's an interesting compensation here. To a first approximation, whatever the temperature is when we suddenly stop emitting CO2 is the temperature we'll have for a long, long, long time afterwards. It doesn't just go back to normal quickly, unfortunately, and that's why there's some urgency. We're on this steep part of the curve. If we're going to do something, we don't have a very long window in which to act. So what are the known risks? I talked about sea level. The thing that perhaps is most worrying, for reasons I'll come to, is increasing extremes of hydrological events. Now, this turns out to be a really basic piece of physics, that when you make the system warmer, places that are wet tend to actually get wetter, places that are dry get drier. Episodes of heavy rain in a place like here, the rain will be heavier. Episodes where you don't have rain for a few weeks in the summer tend to get longer and drier. We expect to see an increase, and arguably have seen an increase in the incidence of high-category hurricanes, which are very destructive globally, more heat stress, and other risks. The thing that keeps me up at night, and I'll come back to this in a minute, is the known influence of climate on destabilizing human civilization. But there are benefits, too, and we would be remiss not to talk about them. At least when you initially increase carbon dioxide, there is some increase in plant productivity. It unfortunately doesn't extend to high concentrations. And we would obviously experience a reduction of health problems related to cold. Okay? Well, we hope we would. But if you sum up over all these effects, because we're so finely adapted to the climate we've had for 7,000 years, the net effects are negative. The IPCC, Intergovernmental Panel on Climate Change, has taken as a whole the range of published evidence indicates that the net damage is likely to be significant and increase over time. So we have increasing sea level. Places like Miami Beach are already experiencing flooding on just normal sort of astronomical high tides. Even in clear weather, as you see in this photograph, they're beginning to have problems. This is happening in many parts of the world. Heat, that's a serious matter. This, again, is a global projection of surface temperature out to the end of the century. The black is the observed temperature. This is the 2003 heat wave in Europe. You see this. That killed thousands of people, that asterisk, and that's going to become quite normal within the lifetimes of the younger people in this room, okay, that we'll have heat waves of that magnitude. That's just an inevitable result directly of the warming of the system. But the thing that I worry about are the hydrological extremes. Rainfall scales with something called Clausius-Clapeyron. It goes up exponentially with temperature, doubling for every 10 degrees increase. As I said before, the wet places get wetter, the dry places get drier. So we actually see both increased incidence of floods and droughts. A large potential effects of this on food and water supplies. And that turns out to be a major national security issue. So we see more floods and more drought. And it sounds paradoxical, but we're beginning to see that already, okay? I think this was taken in Texas. Maybe it's time to take that sign down. So this is the thing that I think is sobering. This is from our Defense Department. These are not sandal-wearing, fruit juice-drinking hippies, okay? These are pretty serious people, and they are seriously worried. And so this is just a quotation from their Defense Quadrennial Review in 2010. Climate change could have significant geopolitical impacts around the world, contributing to poverty, environmental degradation, further weakening of fragile governments. Climate change will contribute to food and water scarcity and will spread the incidence of disease and may spur or exacerbate mass migration. I think if they rewrote that today, they'd say it already is. You know, a lot of the problems we're seeing with immigration pressures in Europe and the US arguably stem from food and water shortages in North Africa and in the Middle East. So we've had dramatic increases in the prices of grain over the last 10 years in North Africa, which can be traced to a serious drought in the Ukraine, which was supplying most of the grain to that region. And history teaches us that hunger and thirst are catalysts for revolution. And they're not necessarily the root cause, but catalysts. So a really wonderful example is the French Revolution. You know, the problems of that monarchy have been around for a long time. They were precipitated by a wheat shortage. This is why Marie Antoinette said cynically, "Let them eat cake," because they didn't have bread. And the wheat shortage is traceable to 2 hailstorms that crossed France in the summer before the revolution, devastating the wheat crop. Right? So we know from the study of history that food and water shortages are very destabilizing politically, and I think we're beginning to see that around the world today. That's what worries me, that's what worries the DoD, and that's what should worry you if you're not worried already. Ocean acidification I've talked about as a problem. Hurricanes, this is a projection to the end of the century of the increase in the cost of hurricanes in 2011 dollars to the US alone. This is the increase in projected for 2030, 2050, and the end of the century. The green, or the blue, is just from sea level rise, assuming the storms themselves don't change, but they will cause bigger storm surges because sea level's higher. The green also considers changes in the hurricanes themselves. So by the end of the century, we're looking at an additional 80 billion a year of losses. This is from a report that was commissioned by the former mayor of New York, Michael Bloomsburg. Now let me finally try to end this somewhat gloomy talk on a note of optimism, okay? Usually when we start talking about solutions, this is where things get really gloomy. Oh, we're going to have an economic disaster. We're all going to have to give up this, that, and the other thing. I don't think that's right. I actually think it's better that we look at it, and appropriate and factual that we look at this as an opportunity. Let me try to describe that. Because there are so many interesting energy alternatives on the horizon, and actually here now to a large extent, and because if we're smart, we can take advantage of it. You know, we have to transform our energy system even if there weren't climate change, because by the end of the century, we're going to be running out of oil and gas, not much later than that out of coal. So, of course, we all have heard about renewables, wind and solar. And the reality of this is that we could get up to of order 30% of our capacity, and that would be great, but it's not enough. And why only 30%? It is simply because we're limited by the fact that wind and sunlight are intermittent sources, and we have to store energy efficiently and distribute it efficiently to make full use of it. Lots and lots of work has gone into this. The consensus of the field is, of course it varies. I mean, places like Iceland and Norway can do 100%. There are places that can do basically 0%. But averaged around the planet, around 30%. Good, we should do it if it makes sense economically. There is some optimism that we can pull carbon dioxide out of the effluent of power plants and other sources, or even pull it out of the free atmosphere away from those sources. And the question, in fact, we know how to do it, and we are beginning to do it. It's just it's very, very expensive right at the moment. For those of you who follow energy costs, right at the moment we think to do this in any kind of global scale would cost about $200 a ton of CO2. And that's unacceptably high. There's no economist I know who would say we could live with that number. If we could get it down to about half, it starts to become attractive. And there are limits to how well you can do this, how cheaply you can get this done. But that is definitely something we ought to be putting a lot more investment into researching, because there is some promise there. But there aren't very many incentives in the United States to develop this. And then there's nuclear fission and fusion, and there are some very bright prospects there. One of the things we know about nuclear fission is that we can, if we wanted to, ramp this up very fast. By ramp it up fast, I mean technically, how can we say that with confidence? Simply because it's already been done. So this is a graph showing just in a sort of a relative scale, years starting in 0 going to 11, for various different countries who began to use nuclear power in year 0 and ramped it up, how fast they were able to do it. This is energy per person in megawatt hours per year. Sweden, France, and Belgium all went sailing up very fast. France went from 0 to 80% of its electricity in not much more than a decade. All right? So if we wanted to do this, we could do it fast. All right? Nuclear power has a bad name, and I have to tell you that I try to stay away from politics, but I end up spending a lot of time talking to climate skeptics. I even went to the Tea Party convention in Nevada last summer. It was probably the most difficult thing I've ever done in my life. Just going to Las Vegas in July is difficult, you know. But I also spend a lot of time talking to people on the left who think that this is a catastrophic power source. It isn't. This is a kind of a gloomy graph. It is mortality of energy in 100,000 deaths per trillion kilowatt hours by the source of energy, so it's mortality. And the source, I hope you can read at the bottom, coal, oil, US coal, gas, hydro, solar, wind, and this is the actual numbers here. So coal is king, and I think people don't realize how deadly coal is. In the United States, the AMA, American Medical Association, estimates there are 13,000 premature deaths in the United States every year as a consequence of the combustion of coal, mostly from ingesting particulates, but also coal mining disasters. It's a deadly power source. Now, if I told you that 13,000 people died from nuclear every year, it would be shut down like that, right? Because it's scary. But we've learned how to live with this. And we should not be happy about that. And the fact that there are people who want to go back to coal is pretty, unethical, given a graph like this. Oil, gas, you're way down to small numbers. Hydro, well, around the world, there's occasionally dam failures. We almost had a spectacular one in California last year. Solar, well, it's a tiny number. What's going on there? It's people falling off their roofs trying to install solar cells. So be careful. I'm very much an advocate of solar, but get a professional to put them up there for you. Wind, this is really strange. It gets to be bizarre. How does a wind turbine get somebody? Well, it's a tiny, tiny number. It's not something to worry about. But things happen like you have freezing rain, the water goes to the end of the blade, it freezes, there chunks of ice get centrifuged off and occasionally hit somebody. I mean, it's a tiny, tiny risk. It's not something you should worry about, but nuclear is lower than that. It's just taking the number of deaths, including all the later deaths from cancers. It's completely dominated by one accident, Chernobyl, which could only have happened in the ex-Soviet Union and had no containment building or anything else. It's really a small risk. It's scary to us, but in the actual practice of it, it has been the safest form of power we've ever come up with. And by replacing fossil fuels where it has, it's estimated to have saved close to 2 million air pollution-related deaths around the world every year. So I think you have to look at risk in this kind of framework. It's relative. It's not, you shouldn't think about it psychologically. You think about the actual numbers, because those are the things that mean something. But we can do a lot better. And one of the things that MIT physicists are working on is taking the old light water reactors, which are the current generation of nuclear powers, and putting them on offshore platforms, which we know how to build. It can be done relatively inexpensively. You have a lot reduced capital costs from doing this, and you reduce the construction costs. They're safer because they're offshore and so forth. And you have a big source of cooling water. You don't need to rob people of fresh water. But we can do much better than that. And one of the things we can do is to do fission a lot better than we're doing it. In fact, arguably, light water reactors should never have been built. They were ideal for submarines, never thought to be ideal for commercial power production. That's a long and sad history. We can be doing that better. For example, there are molten salt reactors that are passively safe. You walk away from them, they basically shut down. They can help process the waste of light water reactors, which is a big issue for them. They operate more or less at ambient pressure rather than the very high pressure of light water reactors. They can run on other fuels like thorium. They're less suitable for weapons, and the estimated plant lifetime is fairly long. Once you have conquered the problem of electrical power production, there are all kinds of exciting technologies to do things like let you drive your cars on ordinary gasoline. Maybe the way to go is electric. I have a Prius. I'd get an electric car if I could afford one. Probably I would someday. But you could actually manufacture gasoline if you have a cheap source of electricity by taking dissolved CO2 out of seawater, which is helping the climate system, electrolyzing water to get hydrogen and combining hydrogen and carbon into hydrocarbon fuels. The Navy already does this, not operationally, but experimentally, and can be done fairly inexpensively. So we can actually make gasoline from electricity, and it's carbon neutral, the process. So let me end here by summarizing what I've tried to get across to you. Several aspects of climate science are well established and have been well established for a long time. The Earth's climate is strongly bounded, that it doesn't go flying off the wheel. We don't have what happened to us, happened to Venus, where we had a runaway greenhouse and all the oceans just evaporated, or we haven't gone into a sustained ice-covered Earth, which is very hard to recover from. But within those bounds, it has been over geological time pretty unstable. Climate science dates well back into the 19th century and is well established. Some of the things that are very well established are the Earth's greenhouse effect. It triples the amount of radiation received at the surface. And it is owing ultimately to greenhouse gases that comprise a tiny, tiny fraction of the atmosphere. The concentration of the most important of these is increased. I have to keep revising that number. It's more like 50% since the dawn of the Industrial Revolution. Beginning with the calculations of the Swedish chemist Arrhenius, 100 years ago, we would predict an increase of around 3 degrees. That's sort of a modified number for each doubling of CO2. That's consistent with the models we have today. The long lifetime of CO2 in the atmosphere, of order thousands of years, means that if we're going to avert these risks, we have to act pretty soon. We can't wait and then try to take it out. It's too expensive. Solar, wind, and fission can replace existing power generation infrastructure in 10 to 20 years. Solar and wind faster, although it's ramping up fast, it's still a tiny fraction of the global power. Fission we can do. I didn't talk about fusion. Somebody wants to ask me about, there's a renewed optimism that we'll be able to do that on sort of like a 30-year time scale. We're going to have to do this anyway, even if the climate doesn't change, because fossil fuels are a limited resource. So why not start a little early? And I think sort of the bottom line here, and what I'd like you to all think about in closing, is not whether this will happen, because it is happening. It's just that China and Russia are the leaders today. China produces most of solar PV. It's a leading producer of wind turbines. They're way ahead of us in advanced fission reactor, building them, not designing them. Okay. By the way, you have a person in the audience here, Bob Hargraves, who's instrumental in pushing this next generation of fission reactor. I'm all for that. You should talk to him. He's the expert, not me. But China is running away with a $6 trillion energy market. It's the global energy market. You know, our GDP is 17 trillion, so it's more than a third of our market. Why would we cede that to another country? But that's what we're doing, all right? So if you don't care about climate for some reason, I hope you do, you just care about our economic welfare, why are we ceding the transformation of the global market to carbon-free to other countries? When we have the innovative skills, we have the infrastructure to do this. We ought to be doing it. There's just about no argument against it. So thank you for being patient. Pleasure to talk to you.
Okay, it is time for the break. I guess the weather did clear up, so I guess we're going to be outside in the on the grass. Professor Emanuel will be signing books out in the back, in the lobby. And please bring your cards and letters, please bring your cards up to the front of the auditorium. Also, please be back at 10:30 and we'll begin the Q&A. Thank you.
good to have it in color because that we'll separate it out.
I did? Where's my ticket? It's up there. Right, check. You know, I thought I had taken, and then I couldn't find it online. I was like, wait a minute, Betsy, I got a ticket. Yeah, so. I didn't. I'm a busy person.
It's a gift.
No, I already paid.
I know, but the second payment is a gift. Like the donation.
You want to use it as a I don't, you know, honestly, I don't mind. I'm a huge supporter of the program. No, you just take it. It's going to Dartmouth College, though. I'm not real keen on so much better, I think. No, I you know, I was like, did I couldn't find it on my ticket. Because I don't think did I get a receipt? Okay, it was a long time ago.
Thank you.
What a great turnout.
Excellent.
Well, the first one was but today we sold
People came.
Really? You know, like
That doesn't always happen. Sometimes we do, like what,
we had a hard time getting something to do. You'd think it'd be easy, weekend on Saturday.
I can count.
You know that
Yeah.
people check out and
Tom
give
still
them
working on the summer series, or is he doing
he's tends to summer series. Some evenings not.
Does he find
And he did I'm not sure, but he did the he's very, very
with William Perry? Okay.
There's good.
He's been traveling a lot. He went to Ireland.
So what's he doing?
Well, you know, he's manic.
I know, but without this,
Yeah. But, yeah. No, I mean, so Ireland and
just
he went with
in and
it.
out.
Yeah. So he, in June, he went to Spain, to Dartmouth. And then he went to Ireland and took Will and Will went to high school soccer and he went over to the ancestors. And then this week he's going to Milwaukee, Chicago, Idaho. And then next week he's going to Seattle. They're going around taking the kids to Concord, they're taking the kids to Concord, Manchester, to play soccer, because they're gonna get recruited to outcome. Play soccer at any college. Run. Like, not even 15. You know, it takes that year. But the parents Division 1 champs. I'm like, oh,
Hello again. Could you all take your seats so we can begin the question and answer period? Thank you.
To the back of the pile.
I can understand that you can just read the first 3 lines if you
Okay.
want to use it. You don't have to do the
And
rest
what
of
about,
it.
and that was another question.
Yeah, as far as I'm concerned, you have the slides. Please
Okay.
feel free
All
to
right.
distribute
Thank you.
them.
Hi, everybody. We've got a bundle of questions, and we'll get through as many of them as we possibly can. But the first question that I have, and I've just asked Professor Emanuel, can we get a copy of his slides? And he said, yes, he'd be very happy to provide a copy of the slides to us. And the next question that I want to ask is one that has been piquing my curiosity as well. When you were a hurricane chaser, what did you learn?
Well, I learned many things chasing hurricanes. I mean, the reason that we fly research missions in hurricanes is to take measurements, to test hypotheses, the usual scientific method, and we, I think, understand hurricanes a lot better than we did 20 or 30 years ago. We basically understand what drives them. There's still a lot of mystery to them. And the eye of a hurricane is such a beautiful place, and I really mean that I think everybody should see one. So after I retire, I'm sort of toying with the idea of starting a hurricane safari. If you'd like to sign up, come and send me a note.
Are you in agreement with Al Gore on climate change, or is he too strong in his advocacy for change?
Well, I don't know Al Gore personally. Of course, I follow what he's doing, and he's a very, very passionate advocate. I think, and this is going outside my expertise, obviously, that he might have played cards a little bit differently and made this much more of a bipartisan kind of effort. So I think inadvertently he may have done a little bit of polarization, but his heart and his mind are in the right place on this issue.
With the U.S. backing out of the Paris Accord, and with China raising its clean energy targets, are we ceding global clean energy leadership to China?
Yes, absolutely we are. I mean, the numbers are very clear about this. As I may have mentioned at the end of my talk, China is the world's largest producer of solar photovoltaics, of wind turbines. They're leading the charge in both old and new fission reactions. They're capturing the market. And I think this is bad for America. I think we should be leading that market.
Will we learn anything about climate change from next week's solar eclipse?
Oh, I think that's a very interesting. I hope we all get to see the eclipse. They're fantastic. I'm not sure that the measurements that are being planned are really going to help us very much on this particular problem, but the sun is a player in climate historically, variations in sunlight. So anything we can do to improve our understanding of how the sun works will help us with the general problem of climate.
We have a ton of questions about nuclear power. What's the single largest obstacle to adopting the nuclear solution that you suggest?
So let me preface my response to all of the nuclear questions by saying what I hope is obvious to you is I'm not a nuclear engineer. I got interested in nuclear because being very interested in the science of climate, one naturally becomes interested in what the route is to solutions. It's very tough to talk about a problem if you don't have some understanding of where the solutions are. So the caveat is, but I think it's very clear that it depends on where you are, but in Western Europe and the United States, it's clearly sort of human, political, psychological objections to it. And the failure of scientists and engineers, I think, not for want of trying, to communicate the real risks and the real benefits, and especially the fact that we don't have to be stuck with 1960s nuclear technology. We shouldn't get stuck there. We can do a lot better, and I'm very confident in that statement. We can, and we should really be trying much harder on that front.
Your slide showed that the mortality from nuclear use is very low. But what about the long-term storage of nuclear waste and the effect on mortality in the future? In other words, what about is the safety of long-term storage for future generations?
So whoever asked that question, you put your finger on the real problem with existing nuclear, at least, which is the waste. It has very long half-life. It's a problem. It's today being stored very safely, but we can't guarantee that's true in the long-term future. But I want to make a very important point about that, and that is that particular genie is definitely out of the bottle. If Western Europe and the US just stopped all of this, we were still left with the fact that Russia and China are not only building old 60s technology reactors, but leasing and selling them abroad. That is scary to me because you've got nuclear waste accumulating in places that we don't have any control over. The US can't stop that happening. What we can do is outcompete Russia and China with safer, clean, carbon-free energy. That's where we should be focusing our efforts.
Would you please address the potential for success with the development of the fusion reactor?
So I'm a good friend of the current director of MIT's nuclear engineering department, Dennis White, and who took me on tours of the various experimental reactors. And there, for the first time in a long time, the people who work seriously on fusion, as he did, are actually very optimistic. There's been a technical breakthrough, and I don't want to get into the details, but it involves the physics of superconducting magnets, which are a very important part of the problem of containing these very hot plasmas. And so they're very optimistic that for the first time that there's a clear route to actually commercial production of fusion. It will take a while. It's not a short-term solution, but we have very bright prospects on, say, the 2-decade time scale for that.
You talked about an offshore floating nuclear power plant. With the rising number of really powerful hurricanes that you've projected, would it be safe?
Well, it's yes, they can be made safe, and the reason that we are fairly confident is that we already build offshore platforms for oil mostly, and a lot of money and work has gone into that problem. And they're safe in terms of the rig actually surviving a storm. I don't think you want to be on, right? They would certainly shut down the nuclear power production in advance of a storm. Fortunately, although hurricanes are getting worse, the forecasts of them are getting better and better, so they would have increasingly good lead times to shut the plant down, I think.
Nuclear reactors produce large amounts of excess heat. Is that a concern for global warming?
So this is an interesting question. Cities in general produce a lot of heat, and a lot of research has gone into whether excess heat in general, whether it's from a nuclear power plant or any other kind of power plant or energy source, is a concern. And the answer to a first approximation is no. It's still a tiny amount of energy compared to the fluxes of energy through the climate system.
Whatever happened to that hole in the ozone layer that we were warned about several decades ago?
The answer is that we fixed it. And this is a really important point, okay? Back then, and it's a little bit hard to understand, but in the 1980s, we had much more bipartisan support for environmental. When this issue of the ozone hole was first raised, there were the usual objections from the chemical industry. This is all nonsense. But the data, the evidence became overwhelming. And we had conservative Republicans, George Shultz, Ronald Reagan, happily pushed the process forward to the Montreal Protocols, which in steps eliminated the production of the chemicals that were destroying ozone. What many of you probably don't realize is just how terrible it would be right now if we had not passed that legislation. We would be in a very bad strait. So there's a very clear answer to that question. We fixed it. We can do it, and we should do it again, okay?
Do you think the Paris Accord was a good, effective accord?
Yes, it was a very, very important first step. It was not a solution in and of itself. These things don't come about politically with one solution. It's steps. Even the Montreal Protocol occurred in steps. It was a very, very important first step. It got unprecedented buy-in from nations all around the world. And it's a terrible tragedy for us that we've withdrawn from it. It may not be a tragedy for the world of climate because the folks like China who will step into the leadership vacuum will push it forward, maybe more effectively than we would have. I'm sad to say that. But it's a loss for this country that we pulled out of it.
Please explain once again how greenhouse gases warm the atmosphere.
Okay. I could have devoted more time. I'll try to do this quickly. So the Earth receives energy from the sun, and it's energy in very high frequency or small wavelength radiation, solar radiation. It's absorbed mostly by the surface, but also a little bit by the atmosphere and by clouds. And for the Earth to be in balance, which it approximately is, it has to get rid of that energy. And it does that by radiating in the infrared. Infrared radiation you can't see, but if you're standing next to a fireplace in the winter, you feel heat. That's mostly infrared radiation. And if there were no greenhouse gases, infrared radiation emitted from the Earth would go directly to space, and we just have sunlight coming in, being absorbed, re-emitted in the infrared. And there'd be a balance, and the surface temperature of the Earth under that balance would be about 0 degrees Fahrenheit, and we wouldn't be talking about it. The greenhouse gases absorb infrared radiation, and then for them to be in balance energetically, they have to re-emit it. So they re-emit it to space, and they re-emit it to the surface. So the surface is now getting more radiation than just sunlight. It's getting infrared coming down from space, or from the atmosphere and clouds. And to be in balance, it has to get even hotter and emit even more radiation. So you have this sort of bouncing back and forth that we call the greenhouse effect. And the bottom line is we get twice as much radiation from the atmosphere and clouds, infrared radiation, 24/7, at night as well as day, than we do directly from the sun. And that's why it's warmer, broadly speaking. That's the short explanation.
How important is methane control to the environment?
So per molecule, methane is a much more effective greenhouse gas than carbon dioxide. But there's a lot less of it in the atmosphere than there is carbon dioxide, so it's not quite as important, but it does make a difference. If we have been adding methane to the atmosphere, and that has contributed to the temperature rise. The other aspect of methane is it's not as long-lived as CO2. So if we stopped producing methane, putting methane in the atmosphere, its levels would drop somewhat more rapidly than the case of carbon dioxide.
We have a question from our colleagues at the University of Vermont. Why are there so many climate models rather than one that scientists could agree on and improve?
Science is not about agreement. Science is more about disagreement. I mean, if you go to a scientific conference, we're mostly arguing that you're very civilized, polite, and we have fun doing it. It's not aggressive. We argue. Science is about uncertainty. There are a lot of weather forecasting models. Now, most of you are aware of the fact that science weather forecasters take very seriously the problem of uncertainty. You will hardly ever get on television or radio or newspaper a forecast that says, this is the way it's going to be tomorrow, period, right? There's an 80% chance of rain, usually not 100%, or 20% chance of rain. So we take that view toward predictive sciences. We're very conscious of the uncertainties. And one of the many sources of uncertainty are the models themselves. They're not perfect. We're keenly aware of that. And one way of dealing with that is you have independent teams, not just in this country, but all over the earth, building their own climate models, and we're constantly comparing them. And that way we get some notion of the uncertainty, that particular uncertainty that's due to the fact that the models aren't perfect.
What will it take to unleash our clean energy industry in the United States?
That's a fairly easy question to answer. The first thing we should be doing, and I say this to Republicans, conservatives all the time, stop subsidizing fossil fuels. It's crazy, okay? Just stop it. They're not in favor of subsidizing anything else. And I would also say stop subsidizing everything else, right? But as a country and as an industry, sometimes it is beneficial for governments to, as a matter of national competition with other countries, is to actually push technologies that look like they have a future. So I don't personally mind doing that. We shouldn't be pushing technologies that are in the past. And so we also need to find a way to make new technologies able to come to market faster. And I mean new wind, and nuclear technologies. A lot of the innovative nuclear technologies are designed here and being built in China because their regulatory apparatus is so inefficient. I don't mean we shouldn't have regulations, but we should have efficient, streamlined ones that work fast. And we don't have that. So those are the big obstacles.
How realistic is it to assume that developing countries like in Africa will take concrete but expensive steps to curtail their carbon dioxide emissions?
I don't think it's realistic at all, to be frank with you. I think the best hope for doing that, I mean, look, the whole problem, the way I look at it and the way a lot of my colleagues look at it is we have these intertwined problems. We have global security, we have global economics, we have the desire to alleviate poverty in places, and we have environmental problems. And in the end, you can't separate them, right? So take India, for example. We can talk about Africa as well. Who in this room would not like to see India conquer the poverty of most of its citizens? But to do that, history teaches us they have to greatly increase their per capita energy consumption. It's just a fact. And we want them to. But if they do that based on carbon, we're all finished. Or we're taking a serious risk. The best thing we can do, in my opinion, for Africa, India, places like that, is put resources in developing new carbon-free technology, energy technology, that makes economic sense for them. And it is doable, right? They should be buying solar, wind, new generation fission reactors from us, rather than leasing old light water reactors technology from Russia, which is what's happening in Pakistan, okay? We have to make it make economic sense to them. Why would we want them to pay double what they should? They don't need to.
Could you comment on progress in battery technology and its possible effects on storage and transportation?
Well, now it's getting very far away from my expertise. I follow it to the extent many of you follow it, and not much more than that. There's a lot of research going on at MIT on batteries. It's a really tough nut to crack. There has been progress. Any of you who drive hybrid cars are beneficiaries of that progress, but nobody is talking seriously that I talk to about breakthroughs that would allow us to do, very, very large scale, order 80%, say, solar energy anytime soon. It may happen, but I don't think we should put, serious money on betting on a miracle. That's the way I look at it.
We had a lot of questions on deniers.
Right.
What are the arguments of scientists and politicians who deny climate change?
Well, I spend a lot of time on that. I spoke to you all today, and you have been a marvelous audience to talk to, but I knew that before I came here. And I mentioned to you that I have gone to other places with fairly hostile crowds. What I find empirically works best for me is what I tried to do a little bit with you here today, is maybe change the subject a little bit away from climate to solutions, because it turns out that for most skeptics, at the core, they're afraid of what the solutions will look like. If they've been told that we're going to crash our economy if we try to fix this problem, who would want to fix it, right? We can't do that. And they've been told a bad story about that, and I've been trying to correct that and get them excited. And at this Tea Party convention, it was sort of an infotainment thing, and I was a witness for the defense, and climate science was on trial. You wonder why I did this, don't you? It's a long story. And I got the audience pretty excited about things like new nuclear, so much so that when they had the jury at the end, I got the jury hung, which was, I think, a big accomplishment. That was fun. It kind of destroyed their proceedings, by the way. I kind of, oddly enough, felt sorry for them in the end.
But did you get their hearts and minds?
I think so. I think if you get people excited about something new technology that's better, clearly better than the old, who wouldn't like, clean energy compared to coal, even if there wasn't a climate problem? They get excited about that. Their resistance to the climate ideas tends to evaporate. But my full-on efforts just to show real dyed-in-the-wool skeptics, the evidence is some people have been saying we live in a post-evidence world, and I find that to be true with some people. So.
Can you, wait a minute, I gotta put the glasses on to read this one.
Uh-oh.
No, let's skip that one. I can't read it. I just installed a pellet boiling carbon neutral boiler to reduce my carbon footprint. Am I wasting my money?
No, I don't think so. It's a complicated problem. Of course, in the short term, when you burn wood, it's releasing carbon to the atmosphere like any fossil fuel, but you're replacing, in the longer term, you're hopefully replacing the trees that were chopped down to make those pellets with wood, with trees that grow and absorb carbon. So in the long term, it's carbon neutral. I don't know much, there are other pollutants that are emitted. How that stacks up against other energy sources, I'm not tuned in enough to this to really say.
How much can individual action, conservation, make a difference, or are we beyond that and need systemic change?
Symbolically, it's really important for people to feel that they're involved in it. When you look at what it would take to lift Africa and India out of poverty in terms of energy, if we're successful, and I devoutly hope that we are, the amount of energy increase that entails is just huge compared to what we could save by conservation. And I'm not saying you shouldn't conserve, but I think you need to be cognizant of that. So conserve by all means, but also be strong advocates for innovative development and research of carbon-free energy, because without that, we're sunk, or we have to live with global poverty, and I don't think we want to do that.
Can you tell us more about carbon collection and sequestration?
Well, the short answer is no, because I'm not an expert. Again, I'm privileged to be at MIT and talk to people who are at this. There's a sort of a thermodynamic limit. There's a lower bound on how much energy you actually have to use to take carbon out of the atmosphere. Now, there are interesting innovations. Exxon, oddly enough, has a new fuel cell that's powered by the heat of effluents from power plants. But in the process of taking that heat out, they're actually able to extract a lot of carbon dioxide from the effluent. So they're actually combining waste heat with waste carbon dioxide in a way that takes the carbon out and actually generates energy, a little bit of energy in the process. Technologies like that give me a lot of hope that that will be an important element of the solution to the problem.
Real or perceived uncertainty in modeling affects political decisions. Please compare the uncertainty of CO2 temp modeling regarding modeling of cloud precipitation and sulfate injection proposals. What's known about the impact of geoengineering?
Well, that's interesting. I'm sort of glad that question came up. I'm always a little bit frightened of it.
I was frightened.
I actually do a little work on geoengineering. Why? Well, we sort of like to know what the options are and kind of look at the uncertainties in that. I don't think anyone's seriously talking about doing it. But one of the reasons to research it is that at least some of the techniques we could do right now, today, and relatively cheaply, so much so, and this is probably the sore point, that very small nations or even very wealthy individuals could do it unilaterally. By that I mean you can inject sulfur into the stratosphere, which is what volcanoes do naturally, by the way, and that cools the climate. It's not a zero-sum game. You can bring the temperature back to where it was, but you won't be bringing global rainfall back to where it was. You'll be making it substantially less than it was before. So quantifying all the risks, I think, are important so that we sort of understand it better. But I think the question was about understanding, and I'd say that there are some elements of it we understand well and a lot of elements that we don't. It's just something that we need to work on more. Not so much with the aim of implementing it, which would be very interesting. I actually had a conversation in a venue very much like this at MIT, in the MIT auditorium, but sitting in that chair was none other than the Dalai Lama. And we were supposed to be talking about geoengineering with him. And when we were finished, he said, "You should start doing it right now," which sort of shocked everybody. But yeah, it's a complex issue.
Well, you kind of addressed the next question, but let me ask it anyway. What would be the effect today of a large or mega eruption of a tropical volcano?
Well, when we know that very large eruptions in the past have affected climate greatly, but for relatively short periods of time. So you can There was a year, 1815, somebody can correct me if I'm off by a year, where it snowed here in New England, where we are here, in the middle of July. And it was generally very cold with a lot of crop failures following a very large eruption. And so they can be very big effects of volcanic eruptions, but the material tends to settle out of the stratosphere. It's the stratospheric material that's really having the effect in a period of a few years, like 2-3 years, something like that. So they don't tend to be long-lasting effects.
What will be the impact of population dynamics in the first world, decreases in first world populations?
So when I said that this is an intertwined problem, and I mentioned global security and poverty and all that, I forgot to mention population, which is a really big part of that. And the recent history of the world shows that population growth, which also drives growth in energy consumption, tends to level off in concert with the elimination of poverty. That is, if you make people wealthier, they tend to have fewer children. For whatever reason, I'm not a sociologist, I don't know why, but that seems to be a fact. And so this has to be considered as well. In the short term, you want countries with very large reproduction rates to consume more energy, if that's a route out of poverty, and therefore a route to leveling off of the population. So that, and I'm not an expert, but people who take these things seriously, the population is central to the whole issue because it is driving a lot of the increase in energy demand, and it's intertwined with all of these problems.
I asked a question earlier about methane gas, and I think this is a slightly different one. It says, I have heard there is an unpredicted factor of methane gas trapped in the permafrost being an extremely potent greenhouse gas contribution being released due to warming. Can you comment?
Yes, I can a bit. Not, again, from my doing the research on it, but there are a lot of people in my department who look at that problem. There's a lot of permafrost in places like Canada, Alaska, Siberia, and locked up in that frost is methane hydrates. And when you melt the permafrost, the methane gets released into the atmosphere. And the problem is, we know that. I mean, we know that there's that feedback in the system, but we're having a devil of a time quantifying it. Because, frankly, we haven't been making very many measurements up there, and that's beginning to change now. The latest papers I've read on that suggest it's not quantitatively that big a problem. It's not going to make a big difference to it, but I think there's still enough uncertainty in that we've really got to try to get on top of that. It's an important, good question to have asked.
Shouldn't we add reducing our consumption of energy to the solutions to mitigate climate change?
Yeah, it should absolutely be part of the solution to that. And again, I mean, why would people reduce their consumption or increase their efficiency? Some out of goodwill, mostly out of economics. So we have to, this is one of the benefits of pricing carbon, which I'm a strong advocate of, because it has deleterious effects. There are these knock-on effects, and even the most conservative governments realize that industry should pay for their externalities, and carbon is now known to be an externality, and it should be taxed as such. That would drive, that would incentivize conservation, and do it globally.
Sea levels are already higher today than at any time in the last 20,000 years. As sea levels continue to rise, what atmospheric and climate implications will there be? Is there any precedent in Earth's history for sea levels this high?
So the answer to the last part of the question is definitely yes. I mean, in one of not the last interglacial period before this one, but the one before that, it's pretty well thought that sea levels were about 30 meters higher than today. And nobody's talking right at the moment about 30-meter sea level rise, but it can happen naturally on long time scales. And it does have long-term ramifications for the climate, but they're fairly subtle. It isn't a huge concern for the kinds of sea level change we're anticipating in the next few centuries.
Related, with the melting of ice and the acidification of the oceans impacting algae, how much additional carbon dioxide will be released or no longer absorbed?
Oh, this is an important question. Right at the moment, about half of the carbon dioxide we're emitting to the atmosphere winds up dissolved in the ocean. The other half winds up in the atmosphere. So the ocean at the moment is a big buffer. And that's a good thing in the sense that it's reduced the amount of carbon dioxide that winds up in the atmosphere. But it's a bad thing, as I described in my talk, in terms of increasing the acidity of the ocean. As you increase the acidity, and for a variety of other reasons, it's thought that you are going to reduce, going forward, reduce the ocean's capacity to uptake carbon. And that means that going forward, that ratio 1/2 may become smaller, and more of the carbon that we burn, a greater fraction of it might end up in the atmosphere.
Again, related to oceans, specify the human impact of sea level rise. What happens to Florida? A lot of us go to Florida in the winter.
Oh dear. As you know, if you've been to Florida, most of the population of Florida is concentrated on the coastline. And even if there weren't climate change, I'm almost, as a hurricane person, which is really what I am, I'm always worried about Florida, particularly Tampa, which has 3 million people, is highly susceptible to storm surges and hasn't had a major hurricane since the 1920s when a few thousand people were living there. So it's going to be the next New Orleans. I hope not within our lifetimes, but it's bound to happen. Climate change or sea level rise just makes that much worse as it goes on. And when we think about sea level rise, the principal reason for it right at the moment is that the ocean is just getting warmer, and water does expand a little bit as it gets warmer. But also increasingly, because you have land ice in Greenland and Antarctica melting and the water runs off into the sea, that effect gets larger. But what keeps us awake at night is that we don't understand the physics very well of ice sitting on land. We observe in the past that sometimes large pieces of ice break off and go into the sea, and you can have rather large, fast increases in sea level. And there is evidence that most of the ice in Greenland was gone during some of the previous interglacials, just naturally. It would take 1,000 years for that to happen, we think, and we hope it would take that long if it happens at all. But that's 7 meters of sea level rise. And if that were to happen, there would not be much of Florida left, I'm afraid. So choose your vacation spots differently.
If electricity can be made and stored locally for less than 5 cents a kilowatt hour, why is it economical to have centralized generation?
Well, I don't really know the answer to that except to say that it depends on the economics of generating electricity. If you could generate it locally for the same price per kilowatt hour that you could generate it with a very large plant, I think it's obvious that it would be better. I don't know about environmental concerns, but absent those, and better to do it locally, right? But if it's much cheaper to do it centrally and distribute it, then that's the way to go. It depends very much on the power source, I would suppose.
In 100 years, if all residences and businesses were self-sustained by solar roofs and adequate storage, and everyone used electric cars, would that climate carbon emit? Would that something climate carbon emitted into the atmosphere?
Yeah, I mean, if we had enough storage capacity and enough to be able to store over sunlight over its intermittency and power homes, communities that way, yeah, that would largely solve the problem. I mean, there are factors involved in the manufacture of solar cells and in their disposal, which is actually an interesting issue, environmental issue, is how do you get rid of old solar cells. Apart from those, yes, but it would take a lot of storage. It wouldn't work everywhere because there are places with not much sunlight, owing mostly to weather. But yeah, wind is a different story because the global rate at which the Earth system generates wind isn't that much more than our current human use of electricity. There's not that much capacity there.
We all remember when we started putting ethanol into our gasoline. Does that make climate change sense?
Well, that's getting pretty far away from what I can deal with. Again, I do occasionally talk to people about that. Apparently not much sense when you take into account all of the other things that have to go into the manufacture of the thing. It's not been a great boon, the ethanol idea.
Could tidal turbine power be ramped up to be a significant contributor to energy along parts of the world's shorelines?
No. And the reason I'm saying that definitely is that, when we landed on the moon in 1969, we put a reflector there. And ever since then, we've been sending a laser beam to that reflector and getting the signal back. What does that tell us? Exactly how far the moon is away from the Earth. Well, that distance is getting larger. Why is that? Because of tidal dissipation. And so we know exactly the number of how much energy is in the natural tides around the whole planet. We know that number very precisely. And it's not much more than human consumption of electricity. I mean, even if we had 100% efficient conversion of tidal energy into electric power, it's not much. Locally, in certain communities with high tidal ranges, it could make sense, but not globally.
What about geothermal as a replacement for fossil fuel?
Again, that's a problem that wouldn't work probably on a global scale, but makes perfect sense in places like Iceland, where you happen to have a very plentiful, easily accessible supply.
We're getting close to the end of the questions. Why are extreme events more likely as the globe warms?
Well, the answer to that question depends on which extreme events you're talking about. I work on hurricanes, and hurricanes actually are a directive byproduct of the fact we have a greenhouse, that we're trapping heat at the surface. It has to get out by some other means. That's evaporation, and ultimately it's evaporation of seawater that drives hurricanes. You put more greenhouse gas in the atmosphere, you need to have more evaporation. The potential intensity of hurricanes goes up, and we've known that for 25, 30 years now. We're beginning to understand the severe thunderstorms, the kind that produce hail and tornadoes. In fact, yesterday, just before I came up here, I was at the thesis defense of my latest graduate student who did his thesis on the subject. That goes up. That potential goes up pretty quickly with temperature. Rain in general, the amount of water in the atmosphere goes up very quickly with temperature, doubles for every 10 degrees centigrade. And so when you warm the atmosphere, a given rainstorm can rain much more. Interestingly enough, there's a global constraint on global rainfall, and that only goes up very slowly as you warm the climate. And the only way to make that work out is to have fewer but more intense rainstorms, which is in general why we expect and are seeing more floods and more droughts.
I know you spent some of your time in France, and here's a question asking what part can France, with its recent history of nuclear power emphasis, be expected to play in the world energy's future?
That turns out to be a very open question, because there are big elements of French society that don't like the fact they're on nuclear power and want to get out of it. And I understand that the current president of France has said he wants to reduce the nuclear proportion from 80 to 50%. I'm looking at my wife, who knows this better. Is that right? No, she says no. Well, that might have been true of anything else, but there is an anti-nuclear movement in Europe, and they shut down all of Germany, or are shutting down all of Germany's nuclear power plants. But the response to that has been for Germany to reopen a lot of its mothballed coal plants and to buy nuclear electricity from France. And so the net result is their emissions went up, even though they colossally increased their solar generation. Their emissions went up, and the price of electricity in Germany went way up and is now the most expensive in Western Europe. So France is an interesting story. It's sitting on an enormous advantage, and I don't know why they would squander it, but I think that whole situation is in flux.
What are the major barriers to U.S. leadership in next generation nuclear development?
Well, I think we have two perils. There are factions on the right, as everyone knows, who don't believe we have a problem to solve. Factions on the left to which nuclear is anathema, period, and over and out, and they won't listen to that. And so I spend a lot of my time fighting the right and the rest of my time fighting the left. A pox on all houses, I say. But it would take really, for the U.S. in modern history, unprecedented leadership, because you don't have a political constituency unless either or both the right come around to understanding that we have a problem to solve and don't mind nuclear being part of that solution, or the left comes, as I hope they will, to realize that has to be, barring some miracle, part of the solution to the problem.
And our last question this morning will be, what do you think is the most effective way to help reduce the risks connected to climate change?
Well, I think, that's a complicated question. I would say that the first thing I would do, if I could do it, is to put a price on carbon to reflect its legitimate externalities. And I would price it according to what it currently takes to extract carbon from the atmosphere. This is how we dealt in a free market society with other forms of pollution, very successfully in the case of ozone, of CFCs which destroy ozone. That's how we did it. We priced them. It costs society in health bills, and coal, for example, should be really priced high because we're passing on the ill effects of that industry to the health industry, and it's costing us a lot, okay? So price carbon and let the markets figure out how to innovate clean energy, and I'm very confident that they would do that.
Thank you very much for your time.
Thank you.